Now let's disable the Windows Defender completely. Before disabling the Windows Defender, let's disable the Windows Update System. For that, we're gonna use these services, and in this service you're gonna scroll it to the bottom and you're gonna find out the Windows Update, and in the properties of the Windows Update, set the startup type to disabled and stop if the process is running. Here I will stop the Windows Update, and after this we're gonna use the gp edit for disabling the Windows Defender. Now in the gp edit, under the administrative templates and under the Windows components, we're gonna look for the Windows Defender antivirus, and here open the allow anti-malware start service to start up with the normal priority, and we're gonna disable it. And for the turn off Microsoft Defender antivirus, we're gonna enable it. And for the other things like real-time protection, we're gonna turn off the real-time protection. We're gonna set it to enable, and for the turn on behavior monitoring, we're gonna set it to disable. For other settings that you wanna explore, for example quarantine, configure the removal of items for the quarantined folder. We're gonna set it to disable, and because this can lead us to delete removal of the malware or the files which we want to, or we want those files to allow on our system. And under the Microsoft Defender application guard, we're gonna disable the turn on Windows application guard in managed mode. And for the exploit guard, we're gonna not change these settings for this, and here we are done with the Windows Defender. So this is how you can disable your Windows Defender completely. Let's install the Flare VM. We'll open the PowerShell and open it as an administrator, and I am gonna go to the desktop folder, and after going to the desktop, I'm gonna copy this that is given in the GitHub repo of the Flare VM. You can just simply search the Flare VM, and after searching the Flare VM, you're gonna get the first link of the GitHub repo of the Flare VM. After opening this, scroll down and you're gonna see the installation instructions. After copying this link, you're gonna paste it, and this will download the installation file. And before running, we're gonna unblock this file using this command. And after unblock, you're gonna set the instruction policies, which are mostly restricted, but we're gonna set to unrestricted. Now it's time for us to execute the installer file, and here you're gonna also require the password. If you are having the password on your Windows, you can simply give it in the parameter of the password, or you can wait for the instruction to execute and you can give the password afterwards. Here I will give the password afterward. As you can see, it is running as the administrator, and after performing some checks, this is gonna now ask for the password. So I wish to proceed, so I'll press yes, and further yes again. Now it has already asked for the password, so I'll fill my password. And as you can see, this is installing every utility one by one. So as this is gonna take a lot of time, let me explain what is Flare VM. In the field of cybersecurity, you're gonna require so many tools, and Flare VM is gonna make this easier for you. Flare VM will install all of the tools that you're gonna require for malware analysis, for penetration testing, for network administration, and for binary analysis, and many more. And this will install all those tools. So I'll meet you after this all is done.
One eternity later.
Finally, Flare VM has installed, and the tools that are installed by the Flare VM, you can find those in your C drive in the tools folder. Today we will look at identifying file more formats and file types. Sometimes extensions of the files are misleading, and you want to know what kind of file you are dealing with. So the basic approach to do this simple task is using an hex editor. In a hex editor, you can simply view the hex version of the data that is stored in the form of bits. As you can see, when you open a text file into an hex editor, the first bits corresponds to the file format, and the last bits are your data. Here, the 68 refers to the H that is written in the file. As I can show you, the file only contains a word that is hello. So in the hex format, it contains the data. What if you are dealing with a multiple files? You cannot open every single file into a hex editor and analyze it. For that, you need some more powerful tool, and for that we are having a Trident. You can download Trident from the mark0.net. You should download the Trid.net. That is the GUI version of Trident. And as I have already downloaded these files, I can simply show you after unzipping those files. And whenever you launch Trident for the first time, you should always add the definitions that are in XML into Trident. And for the analyzing part, you simply need to drag and drop the files. For example, if I show you the zip file that was containing an exe, you can simply, as you can see, no definitions were found in the XML. Here's definitions are there because I have pointed to the parent directory, so I should switch to the subdirectory of the definitions. And now as you can see, the definitions are getting analyzed, and when these will be analyzed, you can see the analysis of the zip file, as this will take some time. And you can see the Trident have analyzed that this file contains 80% of the zip and 20% of the portion is the bin, as it was containing an exe with the txt file. And for the analysis of exe file, you can see the analysis of exe. Now we will look at the process creation and termination of process in an operating system. Process creation refers to the procedure by which new process is initiated by the system. processes are instances of program in execution, and their creation involves several steps, typically managed by the operating system's kernel. To analyze or to look at the processes that are running in the operating system, we will use the process hacker. This is tool that will allow you to analyze and look at the processes that are running in the operating system. Here, the creation of new process usually begins with the existing process known as the parent process. Here, the process hacker named as hacker process hacker.exe is having the parent process as the explorer.exe. The parent process initiates the creation of new processes called the child process. Here, the process hacker.exe is our child process. The operating system, whenever the process has started, will allocate the new process with this data and the stack. The child process in this case is a process hacker.exe may inherit certain attributes from the parent such as environment variables and file descriptors. Now if you double click on the process hacker or child process, you can see various tabs like journal. Here this will provide you the details of the process. As you can see, the current directory for the process and the time when it started and PEB address. Its parent process, that is explorer.exe, and its PID. So what is PID? PID is the process identifier. Here the processes can have same names and their same directories from where they are executed, but PID is the unique identifier to identify the processes. And in the threads tab, you can see number of thread cycles it has been using and other statistics and performance variables you can look at. So now let's see what happens when the process has been terminated. When the process eventually completes its task and terminates, or the termination can occur normally and abnormally. If it is occurring normally, the process finishes with its execution. If it's occurring abnormally, the process might encounter an error or external kill signal. Upon termination, the operating system reclaims its resources allocated to the process, such as memory and file descriptors. So this is how you can look at the current going processes. In today's video, we will talk about virtual memory. Our computers generally are having low physical memory. Still, we'll run the applications that require much higher memory than our physical memory. This is made possible by the virtual memory, that is a management technique that allows an operating system to use more memory than is physically available on a system. It does this by combining the computer's physical RAM with the disk space, creating a large virtual space. This virtual space can be much larger than the physical memory, allowing applications to run even if they require more memory than that is physically available. Now let's check what happens at the back in the memory when a process is running. We will monitor this process by the process hacker. Let's check the memory of the process hacker itself. Here you can see the process hacker displays us the base addresses of the memory that is allocated to an process, and the type of memory that is allocated with their size and the permissions or privileges that are set to that particular address space. Here, mapped memory type. This refers to the memory mapped files where files contents are mapped directly into the virtual memory. When an executable file or DLL is located into the memory, it is mapped into the process address space. This allows the OS to load and execute the file without reading. Private memory refers to the memory that is used exclusively by a process that cannot be shared with the other processes. And after the process mapped, you can also find an image memory type. The image memory typically refers to the memory used to load and manage the executable files and their associated resources. When you further open the image memory type, you can see whether it is commit, reserved, or free. What does commit, reserved, and free mean? Commit memory refers to the virtual memory that has been allocated by the OS to a process and is guaranteed to be backed up by the physical memory. While the reserved memory refers to the virtual memory that has been set aside by a process but not yet committed. Free memory refers to the virtual memory that is not currently used by any process. When you open any memory, you can see its ASCII and the hex that has been stored into the given addresses. This is not a much better way to see the ASCII representations of an memory address. To view the strings that are available in the process that has been running, you can use these string options, and this will view you the strings or the ASCII representations in the memory addresses. As you can see, this is quite helpful when you are dealing with the malware, as you can filter those if it is containing something like HTTPS. This will indicate if a certain application is redirecting or using an URL to connect with. So this was all about the virtual memory and how you can observe the memory into an process hacker. In this video, we will talk about PE file. Now let's break down the structure of the portable executable file, which is the file format for executables, object code, and DLLs in the Windows operating system. It includes header and sections that define the executable code, data, and resources. As you can see, this is the breakdown structure of an PE file, where the first we are having a DOS MZ header, then the DOS stub and the PE file header. Then we are having a section table, and after the section table we are having the number of sections that are present in the executable file. Now let's understand this more by examining a single file. For this example, I am using a simple hello world file which just prints an hello world. For examining purpose, I will use tools like CFF Explorer and Hex Editor and an X32-bit DBG, that is a debugger for 32-bit applications. So first let's look at the CFF Explorer. Now if you see at the DOS header, in the first column we are having an eMagic that is having a value of 5A and 4D. These are the first two hex in the hex editor, which represent the MS, which represents that this file is a DOS file or a PE executable file. And the numbers that you see in hex editor are 4D and 5A, while the numbers or the value in the row is 5A 4D. This is due to the little endian that is followed in the Intel architecture. Now, after this, in the hex editor, you can see that it also contains that this program cannot be run in the DOS mode. As we have already seen in the structure, that DOS stub contains the display warning that if file can be run into the Windows or not. And this is the hex that contains the value of the warning about the DOS file. After the DOS header, we are having the init header that is just after the DOS header, or you can also call it as a PE header. If you see at the last value or the last row in the DOS header, that is elf new, which contains the value address of 80. And in the hex editor, if you check the offset 80, you will find the PE flag that indicates that this file is an PE file. Now this field at offset 0x3c holds the file offset to start the PE header, indicating that where the actual PE file begins. As you can see, it contains the value of 80, and if you check the offset into a file hex editor, you will find the same value, which indicates that from here the main PE file begins. The init header marks the beginning of the PE file proper and includes a signature, followed by three main components that are the file header, optional header, and data directories. The file header describes the target machine, as you can see in the first column, or in the second row, the target machine and the number of sections. Here the number of sections contains the value 2, and if we jump over to the section headers, we are having the sections .txt and .data. And if you are more familiar with the assembly language, there are major three types of the sections. First is text section that contains all your executable code, and the data section contains the initialized data. And the third section that has not been seen in this file is BSS section, as this is a simple hello world file that doesn't require an uninitialized data, as the BSS section contains the uninitialized data that will be initialized after the program executes. And if we check the characteristics of the text section, you can see that it is an executable, or the executable flag is checked, and it is readable and is not writable, while the data section is only readable and writable, is not executable. When you are dealing with the malware can be injected into the data and text sections, or they can also play with the number of sections to increase the value and to add other sections into the section headers, which will make an unwanted code to run through your program. And in the file header, This also contains the time data stamp and the number of symbols or the size of your optional headers. In optional header, don't go by the name of optional. This is a very crucial header. It provides information about memory layout, entry point and subsystem. As you can see, the address of entry point is 401040. This is relative address. Image base is the preferred base address for the loaded file in memory, which means the actual entry point is the addition of address of entry point and the image base. If we check into a debugger and if you load the program and you run it, this is the entry point of a program. And if you see the image base, that was 4 and 5 zeros, as you can see, double 0 and 4 and addition to 1 0 and 4 0, which is the same here. This is the difference between a relative address and the actual address that is loaded into a memory. And the size of image is the total size of the loaded image. The subsystem is the type of subsystem required, like Windows GUI or the console. It holds the value which indicates the type of system. Like here, the 3 contains is indicating to the value, which means the Windows console, as this program doesn't require any GUI for its execution. The magic specifies the format, example PE32 or PE32 plus for 64-bit. Here, this means that this whole program is 32-bit executable. Now let's jump into the data directories. This header specifies the locations and the size of important tables and strings, like important import and export tables. Now let's check out the section headers. This describes each section in the file which would contain code, data or resources. The name field of the section includes text for code and data for data. And virtual size is the size of this section in a memory. And virtual address is the relative virtual address where the section starts in a memory. Understanding these components is very crucial for reverse engineering and malware analysis. Malware analysis is the process of understanding the behavior and the purpose of any suspicious file or a URL. This process is divided into 2 primary approaches: static analysis and dynamic analysis. Static analysis involves examining the code and the structure of a malware sample without executing it. The goal is to gather the information about the malware, such as its functionality, the data it manipulates, and its intended targets. The key concepts in the static analysis are hashing, embedded strings, and PE header. Hashing generates a unique fingerprint or a hash of a file. This fingerprint can be used to identify a known malware by comparing it against a database of known hashes. If a file hash matches with the known malware hash, it's likely that the file is malicious. Hashes are also useful in verifying the integrity of files. Embedded strings are the sequence of readable characters embedded within the malware binary. These strings can reveal clues about the malware functionality, such as URLs, file paths, IP addresses, and error messages. Analysts often search for suspicious strings that might indicate the malicious activity, such as references to a system commands. PE header is a crucial part for the Windows executable files. It contains metadata about the file, including the information about sections and other attributes. Dynamic analysis. It involves executing the malware in controlled environment, such as sandbox, to observe its behavior. This approach helps in understanding how malware interacts with the system in real time. The key concepts in dynamic analysis are monitoring changes and behavior monitoring. In monitoring changes, you track the changes to the files and directories malware might create or delete or modify. You also observe the network activity, communications, including any DNS request, HTTP traffic, and attempts to connect to a remote servers. Behavior monitoring is to monitor any API calls made by the malware to understand what actions it's performing. For instance, calls to open process, write process memory, and create remote thread might suggest code injection techniques. Observe the changes to a memory, such as a new regions being allocated, modified, or freed. Malware often uses techniques to detect if it's being analyzed, such as checking for debuggers, virtual machines, or sandboxes. Here are some tools for malware analysis, both for the static analysis tools and dynamic analysis tools. TriadNet is a file identifier that analyzes a file's binary signature to determine its type. ExeInfoPE, a tool for analyzing Windows PE or portable executable files. It provides information about the compiler used, the packer or protector applied, and other file attributes. Bin.txt, a simple tool to extract ASCII and Unicode strings from a binary files. Strings. It's similar to the bin.txt, the strings command line, and extracts printable characters from binary files. XOR search, a tool designed to search for strings in files that may be XOR encoded. CFF Explorer, a tool for exploring the structure of PE files. It allows for detailed analysis of headers, sections, and resources. PE Studio, a powerful tool for static analysis of PE files. It provides detailed information about the file, including the potential indicators of malware, suspicion sections, and non-malicious signatures. HashMyFile, a small utility that allows you to calculate MD5, SHA1, CRC32 hashes for one or more files. Now let's jump into the dynamic analysis tools. Regshot, a registry snapshot tool that allows you to take two snapshots of the registry that and compare and to detect the changes. Autoruns display all program configured to run during the system boot up or login. It is useful for identifying persistence mechanisms that malware might use to maintain a foothold on a system. FakeNet, dynamic analysis tool that simulates a network environment, capturing and redirecting network traffic. The traffic that has been captured by FakeNet can be analyzed into Wireshark. Process Monitor, or the ProcMon. It is a real-time file system registry and a process activity monitoring tool. ProcDot, a tool that visualizes the data captured by a process or a monitor. It creates a graph that shows the relationship between the processes, files, and registry keys. There are furthermore techniques for the malware analysis, such as reverse engineering, memory analysis, and automation. As memory being the main part that gets infected under the malware attack, understanding and analyzing the memory can be much more effective during the malware analysis. And the reverse engineering, when you reverse engineer exe file or the malware, you can understand its properties and the task it is trying to reach. You can use tools like Ghidra and IDA Pro for the reverse engineering. So these are the major 5 areas that you should focus during your analysis process. You should check on the modifications if they are made to the file system or the registry. You should check the network traffic that is generated during the malware. And you should also check if the malware auto starts and any other process that it launches. In this video, we'll do a dynamic analysis of malware. For this, we'll use process monitoring tool and fakenet to monitor any network request made by the malware, and Rekshot to take the snapshot of our windows. So first let's fire up the process monitor and let's pause process monitor for time being until we run our malware, and let's clear. Now let's launch fakenet. This will act as a fake server. It will store the data into pcap file that we can analyze into Wireshark. Now let's launch Rekshot and we'll take the first snapshot. Before doing that, let's change the directory to C, and now let's take the first snapshot. So our first snapshot has been completed. Now we will run our malware and wait for 2 or 3 minutes. It has been 7:57 and we'll run until 8 o'clock. Then we'll take the second snapshot and we'll compare the changes. Before that, let's resume our process monitor to see all the changes made by malware, and it has started taking the results. Let's fire the malware. Just after launching malware, it has deleted itself and it has made a post request to an host at port 80, and connection is set to close, which means this is just sending the data and it is not hoping to receive any data. And the content length is 80, and this is the content which is encoded. As you can see in the process monitor, we can just simply filter as you can see when I search budget report exe, which was the name of our malware, it has shown some of processes created by it, such as creating file, closing a file, and some another request about 3 minutes, and there was no other request made by malware. And now what we should do, we can just take the second snapshot. So there has been another request that is made. It is quite same to the first one, where the data or the value that was sent is quite a different. As you can see, in the previous it ended with the 69, now it's 67. All other details are same. It has been sent to the same address, to the same port number. You can see second snapshot has been taken. Now let's compare the results. This will be a simple text file showing the results or the changes that were made between first and second snapshot before running the malware and after running the malware. So if you see the results, there were 0 keys that were deleted, but it added 4 keys. This can be keys that would be added due to adding the persistence, so the malware could start on the auto start of the PC. One folder was added. There were 6 files that were deleted and there were 6 files that were added and 1 file that was deleted. 33 files were modified. Total changes 93. And let's check out the output. So these are the 4 keys that were added, and these are the 4 values into the keys that were added. This single key is containing a large amount of data, and the folder that was added is into roaming, and there were one file. As you can see, the file that was deleted is just the malware because it deleted itself. So this is more detailed version of the changes that were made. And now let's check pcap file that was created in fake net folder, and let's analyze it into Wireshark. And if you search HTTP, you should be able to find that request that was made by the malware. So this is the post request, and there were 2 requests that were made. So this is the first and this is the second. So let's open this. You can check this value out. You can just copy from here the value and check it or analyze it further. The value of C is just some gibberish. So first we'll filter out. We'll click on the filter icon, and in this we'll select out the process name, and we'll check the process to be budget report. Excluding all other processes, and we just want budget report to be shown, and let's apply that. Now we'll apply another filter from the operation section. It created a write file operation which allowed malware to move from a desktop folder into a roaming folder. Now let's apply this. So this is the processes that were made by the write file operation, and similarly you can also add another filters. But before that, to analyze it more further, we'll use a tool that is proc. For that we'll save into a CSV file and into desktop again. we'll set it to all events and let it export. Until then we can run our proc dot. This is taking quite a bit of time. Now it has exported into CSV. Now let's import our CSV file. So it will start analyzing it. So now the analysis of procmon file has started. The file has been analyzed. So in this we will just select our budget report with PID 5424 and we'll just refresh it. And now this will generate us an interactive graph for our malware and we can track its processes. So our file has been analyzed and proc has been showing us the budget report exe. For zooming it you can use control and scroll. So this will zoom out. For dragging you can just use your left click and drag around. So now you can see a diagrammatical, or you can say information through a graph. So this will be much more easier to analyze. So this was the file that was created by the budget report. So this is how you can analyze your malware in proc. In this video we'll do a complete analysis of a malware using static and dynamic tools. First let's check out our malware, that is financials xls.exe. Let's check this malware into TriNet. It's 55% exe, 13.4% DLL and 10.2% 16-bit executable and 9.2% generic 32-bit executable and 4.1 OS2 executable. Now let's analyze this file into exeinfo.pe. This provides information about entry point, file in offset, linker info, file size, EP section and subsystem, that is Windows GUI, the lammer info, which is info about if the file is packed or unpacked. As you can see, this file is packed and the software is suggesting us to unpack the file using UPX. So let's use UPX in CMD to unpack this file. And now let's unpack the file. Let me confirm the spellings once again. As this can lead to further mistakes. I mistaken, the command is UPX. And now Let me copy the file path once again. So the file is unpacked. And let's analyze this file, the unpacked file, into exe info p. And in lammer info section, you can see this file is the original file of the malware, as there is no unpack information about this. Now let's use bin.txt to analyze the embedded strings in the malware. First we are having the warning flag about the PE file that this program cannot be run in DOS mode, and then we can see there are some functions like read file, write file, and a delete file A with create file A and copy thread. The malware can use write file and read file and the delete file to move its location and to make a copy of itself into another directory. And it also uses functions like exit process and terminate process to take a control over some processes, and there are functions for the modification of registries which can allow the malware to have persistence over your PC, making the malware to auto start whenever the PC starts, or making the malware decide when to auto start during any process. And there is some HTML code with some JavaScript language, and there is simple text. Your computer is in danger. Windows Security Center has detected spyware adware infection. It is strongly recommended to use special anti-spyware tools to prevent data loss. This is this can be used by malware to trick the user to download any third-party app or third-party files. As you can see, it also uses get request to download something from host download.bravesentry, and there is another request to the same server. So this gives us quite a lot information about the malware. The first key point to note is that malware is using functions for the file modification, making it to delete files and move the files from one directory to another. The second key point is that it is using the registry modification to make its persistence. Third, it is using the network to download some files into your computer. So I don't see any useful information. Again, it's the same information like read and write file. The information has repeated itself. Maybe it's creating a file, a similar file to itself, which does the same task. It's creating that file into another directory. As you can see, there is information about a directory C Windows X update.exe. This may be the another file that it will create and store this whole information inside that. And now this is the end of the file, and there is a cancel operation, as this could be the last instructions that could be led by malware. Now let's search some encoded strings using XOR search. As bin.txt can only show you strings that are not encoded, let's use XOR search to decode strings using a brute force. Now we'll give the file name, that is unpacked.exe. Now we'll give a parameter for the string that we wanna search into the file using brute force. So first let's check for the HTTP. There are no special results in this information, as the first result, that is download Braves entry, we have already seen that in bn.txt, and another that is found using XOR 20 is not quite useful. And for the next operation we'll use this as a keyword, because if you remember the bin.txt, let's import the file, there was the DOS warning, this program cannot be run in DOS mode. If the file is creating any another file and the information about creating the another file is encoded, so this command can lead us to exploiting that information. There was only one search entry about this information, that was this program cannot be run in DOS mode, that we have already seen in bin.txt, that was not encoded. So there is no much quite useful information that we can get through XOR search. There are very less encodings used in the malware. Now let's use PE Studio. Let's fire up the PE Studio. Now let's import the unpacked version of the malware and let it run. It will analyze the let's open another instance of PE Studio to analyze the unpacked version. This will give you an idea how this is less efficient to not to unpack the file. If you head to the import section in the both information, can get the very minimal information in the packed version of the malware, while in the unpacked version you can get quite a big information about the import section. There are quite 20 flags that were detected in the unpacked version and only 2 being detected in the packed version. So this is first thing that you should check, is that if the malware is packed or unpacked. Now let's study the unpacked version. Let's head to the indicator section. As you can see, the level of compromise is coming from the text section, indicates that this is writable. So what really is the problem with writable? The text section should never be writable. It should only be readable and executable. And text section is also self-modifying, which means malware is using self-modification techniques to change its structure. and other information. And it is also using VSL, which is Web Socket Library, to connect to the server. As we have already seen, that was the Brave Sentry, the host that was the host that malware was trying to connect. Now let's head over to the section, text section, that is writable and executable and is self-modifying. And now let's head over to the library section, that is using the Windows Socket library, and to the import section. Here you can find that there are the 4 registry keys that we have already seen in the bin.txt, that it was trying to use the registry functions for its persistence, especially this registry set value exa. It is the biggest indicator for the persistence, and it is using the write file and delete file operations, as we have already seen. Now let's use the string section. It's about the same, that read file and write file operations. So why are we seeing these same things in the import and string section? This is maybe because it was trying to create another file, and the data that it's trying to write in that file is stored into the strings section, or that is just stored in the text form. Now we'll do a dynamic analysis of the malware. For that, you should always follow some precautions. First, there should be no internet connection, because this can be quite harmful when you are in your workplace or connected to any public network. For next precaution is that you should never run the malware directly to your main host. You should always use any virtual system. Like in this case, I'm using a Windows 10 into VMware. Next, we'll launch Procmon, which is a process monitoring tool. Now we'll pause the Procmon and clear all the data, because we'll use this when we are running the malware. Now let's fire up the fake net. The traffic that will be generated using this software will be stored in the pcap file that we can analyze further using Wireshark. And now let's use Regshot. Using Regshot, we'll make a snapshot of our windows, and we can compare the changes between the first shot and the second shot. And first shot will take before running the malware, and second shot after running the malware. So we will able to observe the changes that will be made by the malware. It will take quite a bit of time for first shot to complete. So our first shot is completed. Now we'll run the process monitor, and we'll run our malware. So as you can see, this is pop-up that we just saw, that was sent by the malware. This is the same information that we observed in the using bin.txt, that was used to trick the user to download any malicious file. And you can see it is also sending a GET request. that is to the same host that we just saw. That was the download.bravesentry.com, and for the first instance it's only just sending the get request. Now let it run for 2 or 3 minutes. Now it's about 2 minutes from running. Now let's pause our process monitor, and now we'll take the second snapshot. In the meantime, second snapshot is getting completed. We'll just save the data that we just captured into CSV file. But just doing that, just make sure in the option and the select columns you have this thread ID enabled. This will be used in the proc dot. And now let's save, and we'll use the all events and CSV as the format. Sorry, I just did a mistake. I'll just save this into desktop folder. So as you can see, the second snapshot has been done. For we'll just compare it will just take some time. In the meantime, we can just export that. We just exported our CSV file, and in process monitor you can also use the filter option to check out or observe the malware. So first we can just use the operation. No, not the operation. We can just use the process name. In the drop down we can search for the unpacked. There is a unpacked.exe, and now we'll add it, and you can see it has been filtered to the number 1000 from Slack. Now you can also use another filters like the operation, and we can use a write file here, write file, and this will also increase the it to 1. And another filters you can also apply that were use the operation. Here we will search TCP, and we'll add it, and we can also search UDP. And this can also, you can try different filters and search through them. This will give you quite information about your malware, but we'll use proc.dot to analyze those results. For time being, let's compare the results from the first shot and second shot. So there were 20,000 keys that were deleted, and 8 keys were added, and about 24,000 values were deleted. 18 were added, and 33 were modified. And folder, there were 0 folders, that were deleted. So modification through the folders was 0, and there were 0 files that were deleted and 12 files that were added. So maybe that file that was added into the Windows folder, it may be one of them. And there were about 44,000 changes that were made. Let's compare, or maybe let's check out in the text format. So these are the keys that were deleted. You can use this data to report, and let's just head it down. There was over 20,000 values. Let's head down, and it's a quite a big number. So it was quite here. So this is a detailed information about your files and the folders that were deleted and the values that were modified. So the files that were added, we can just simply check in this. So we'll just simply, so this was the file that was added, and one more that was installed dot dat that was added into the roaming folder in the app data. And there are other files that were added, and there are 34 files that were modified. So this is a quite detailed information about everything that was done by the malware. Now let's analyze the network information that was generated by the fake net. So you can also take a screenshot of this information, but we'll just use the Wireshark. In the Wireshark, we'll just simply import the file and we'll search for the HTTP. In the HTTP, we'll just simply search for the website that it was aiming for. As you can see, there is a GET request and it's download. Maybe it's the same. Yeah, it's the host is a download.brave sentry. There are other more GET requests. We'll just analyze this one. We can just follow the TCP stream. Now you can see that this was the GET request, and this was the response from the fake net that was acting as a fake server. So the fake net is just giving information about itself. The fake net is a next generation dynamic network analysis tool. So this is the quite information about itself. So this was the GET request that was requested from the malware. So this is how you can analyze your network traffic that was made by the malware. Now let's use prog. Using prog, we'll graphically analyze the changes made by the malware. First, let's load the CSV file. Now we'll click the launcher to analyze the procmon file. In the program process name section, we'll select the unpack.exe and we'll click the refresh to generate the graph. you can hold control and scroll to zoom and left click to drag around. So this was the unpacked.exe that we was just launched, and it created a thread 77204, and so this created a persistence auto start into the Windows update loader. That was the file we just saw, that was in the C drive into the Windows directory, that was xpupdate.exe. So what I can just assume is unpacked.exe and the xpupdate.exe are the same files, and there was another thread that was created by the 7204, that was 48112, and it created a file into the roaming section that was install.dat, and we are just getting the same thing from the unpacked.exe, and it also created another persistence into the registry using the registry named con, and this registry created another file. Now using this registry auto start, the file or the malware into the desktop folder will run, and this again created another registries. These are the whole list number of the registries that were created, and it was created by the thread 5788. So this was the information about the malware. So this is all. So this is how you can analyze your file using proc.dot. So now this was the whole complete analysis of the malware that you can do, and the information that was discovered, you can use that information to report the malware. In this video, we are looking at LokiBot that employs Trojan that can steal your username, passwords, and other credentials. So this is our malware. I have renamed it using the .bin extension to avoid unwanted clicking. Now let's analyze this in TriNet. Now let's import. So it states that it is a Windows control panel item. So let's open this in exe info. Maybe the file is packed. So the exe info has stated that this is an AutoIT file. AutoIT is a scripting language that was designed for automating Windows GUI and journal scripting tasks. So it is suggesting us to use exe to auto decompile. So let's use that to decompile the malware. Now it has generated the script file contains the AutoIT script. The code in the AutoIT code has been obfuscated, which means the code is harder to understand and the variable names has been altered. So now let's scroll down for some meaningful information. This is the second payload that we have located, while the above all the auto IT script was the first payload. But since this second payload has been encrypted into shellcode, we cannot analyze this now. We need to run this into action and use the memory to dump the unencrypted code from this shellcode. For that we'll use the debuggers, disassemblers and decompilers. For this we'll use Ghidra and x32-bit DBG. Before that, let's check this file into PE Studio. If you head to the indicator section, you can see there has been embedded code that we have already seen, that was the shell code which was being appended multiple times into a variable. Now, and there has been some Windows libraries indicated as flag. One of them is a Windows Shocker library. We have already seen this library as a red flag in our previous malwares. And there has been another library related to the internet which is wininet.dll. Now let's head to the import section. 5 registry related functions that are being used. The registry set value exw, this can be used to create the persistence. Now let's analyze our malware using disassembly and decompiling techniques in Ghidra. So first let's fire up the Ghidra. We'll also store all the files related to the malware in one directory. Let me create a directory named malware. I'll just simply close the tip of day and let's rename it malware s3 and let me move the files. Now let's create a new project. Create it a non-shared project and let's change its directory to the malware. Let's select the directory. Let's name the project malware and click on the finish. Now let's import our malware into malware folder in the Ghidra. It will take some time to import. If you see in the tool chest, you have a code browser, the debugger, an emulator, and a version tracking system. For our use case, we'll use code browser to see the disassembly and decompiled version of our code. So we have the result summary of our malware. Here you can see useful informations like the minimum address, maximum address that the malware can use. This refers to the memory addresses. We also have here the MD5 and SHA 256 hashes generated for this file. Now let's close our result summary window, and now let's open our sample bin in the code browser. Now we will analyze our malware, and for the analysis options, let's keep this to the default, and this will take quite a bit of time for analyzing. As you can see, the for time being, let me introduce to the program trees. Program trees contains the number of sections that this malware uses, and in the symbol tree you can find import and exports. The import section includes the functions or the files the malware will use, and in the export you will find only the entry function. Now our malware has been analyzed by the Ghidra. Now let's look into the functions. You can see the entry function. This is the entry point of the file. Now let's enter to the entry function, and in the entry function you can see a call made to the security init cookie. Whenever you are disassembling the file, you should always look for this security init cookie, because just below the security init cookie you will see a jump call made to a function, and this function will take you to the main function. So let's open this function, and in this function, if you scroll down, you will find a function that is taking 3 parameters. Because this is taking 3 parameter, this is likely to be our main function. If you search msdn main, you will head to this website where you can find the information about main. The main function takes 3 parameters, and you can also see the detailed information about all these 3 parameters. The optional EMVP parameter is an array of strings representing the variable set in user's environment, while argc is an integer that contains the count of arguments that follow in argv, and argv is an array of null terminated strings representing the command line arguments entered by the user. By this you can understand that argv is an array representing the inputs given by the user, while argc is the number of inputs, and argvp is related to the user's environment. Let's edit this function. Now we'll paste the syntax that we copied from our site, and since Ghidra doesn't recognize these brackets, we'll use an asterisk and press OK to make the changes. Sorry, this isn't in the function. Changes has been made in the disassembly panel and in the decompiled panel. Now let's move to the main function, and in the main function you can see the main function, different functions within the main function. You can also view this using the function call function graph. This will give you the graphical representation of the functions. Since this was our main function and there are different functions within this, so to view the different functions within the functions, you can use this plus icon, and this will load the functions within that function. This will take quite a bit of time. Yeah, you can see number of functions within a function. You can use scroll to zoom in and zoom out, and click to drag around. You can also use another window called function graph. This will give you graphical representation with the code or the disassembled assembly code of a function. Within these functions, let's open each of them one by one. To return to the previous function, we'll use this icon, and now let's open the next function to check any other to see quite useful informations. And here you will find is debugger present function. This will detect if our debugger is, if we are using any debugger or not. It will return 1 if it detects a debugger, and 0 if it doesn't detect an debugger. Since to analyze this malware we require a debugger to dump our memory, to dump that shell code into the memory that we previously seen in the sample auto file. But we also need to bypass this function. To get more information about this function, you can search is debugger present MSDN, just like we did with the main function. Now we will use a debugger to exploit the is debugger present functionality and to dump the shell code in memory that we have previously seen in auto IT file. Now let's launch our X32DBG, that is a 32-bit debugger, and import our file. Now we have to track our is debugger present function. So the address of is debugger present function is 403b7a. But since the window uses ASLR with automatic space layout randomization, the base address of process is randomized. As you can see, the base address in the X32-bit debugger is 1A 4 zeros, and the base address in Ghidra was 0040 and 4 zeros. So we need to add 3b7a into the base address in debugger, which is 1a and 4 zeros. So we'll jump to the expression This was the base address of debugger. Now we will add 3b7a into this, and this will take us to the isDebugger present function. Now we'll add a breakpoint here. Value in EAX before running the isDebugger present function is 9f double f double c. After you step over the isDebugger present function, it returns the value 1 into EAX, which means it has detected our debugger. We'll bypass this by editing the value to 0, which means the isDebugger present function has returned false. And after the test comparison, if the value in EAX is 1, it will execute this jump function, which is jump if not equal. If the value in EAX register is 0, the jump function will not be executed. Now if you step over, the jump function is not getting executed. Now we will add a breakpoint to the virtual alloc function. Now if you go to the breakpoints, you will see a breakpoint added to the virtual alloc. This function is responsible for allocating the memory, for allocating virtual memory to a process. Now we will run and we'll wait for breakpoint to hit. Now it has hit the breakpoint at the virtual alloc. Now we will step over the function. Now this function will take us to the virtual alloc, which is the main function for allocating the memory into a virtual alloc. As you can see in this disassembly, the main virtual alloc functionality lies here when it calls the virtual alloc, and the address of the allocated memory is stored into ESI. Let's add a breakpoint here. Let's run. You can see that before this function, before this instruction, the value in ESI is zeros, and after this instruction, the value in ESI contains the address of the allocated memory. So we will follow this memory into the memory map, and you can see in the protection section, it contains the privilege of execution, read and write. And now we'll head over to the CPU again, and we'll follow this address into the memory dump, and you can see the memory contains all zeros. Now we have located the memory address where the malware will unpack the shellcode and execute the shellcode from that address. Before it executes the shellcode, we'll add an breakpoint, which is an hardware execute breakpoint. After the malware unpacks the shellcode into the memory, and just before it executes, the breakpoint will hit, and we will be able to retrieve the unpacked shellcode. This will also save us from accidentally running the malware. Now let's look at any other functions allocating memory. We have hit another virtual alloc function. Before we step further, let's take a record of the addresses that virtual alloc has allocated for the dump of the shellcode. And for the next, we'll copy from the ESI. Then it is another address for the virtual allocated memory. We'll copy the value and we'll follow in the dump, and we'll hit a breakpoint here again. The hardware execute. You can see the breakpoints added in the hardware section. If the payload gets to execute, we have already set the execute breakpoint. Now let's run our malware. In our memory map, the address 36A in the memory, the address from 3720 and 4 zeros has hit the breakpoint of execute, and the malware has unpacked itself into the virtual memory. Now we'll use another tool called process hacker to investigate this address, which is 03720000. Now let's fire up the process hacker. We'll scroll to the x32-bit dbg sample bin, and in the memory section we'll look for 37200. And you can see the permissions are read, write and execute. Similarly, we have the another again, which was 03680000, and it also have the permissions for the execute. Now let's investigate the sections. We have more unpacked data in this memory section, so we will save this into the bin file, into the download. So now we have successfully unpacked the shellcode.